So we have a dipole um, which has the magnitude 17 millicoulomb, and it's put into an electric field which is in the x direction with a magnitude of 87 kilonewton per coulomb, and the dipole orientation is given with respect to the x-axis is making an angle pi over 6 or 30 degrees with the x-axis. So the question is how much work is required to rotate the dipole until it is oriented along the x-axis, which is parallel to the electric field. So let's put our electric field in the x direction, and this is x-axis, but the electric field is also oriented along the x-axis, and the dipole is making an angle of 30 degrees with the electric field, or electric field, since it's in the x-axis, the dipole is making an angle 30 degrees with the x-axis also. So this is our dipole P. Okay, and what is given in the problem is that the magnitude of the dipole is 17 times 10 to the minus 3 coulomb. Okay, and since the electric field is also given 87 times 10 to 3 I kilonewton. Yeah, it's kilonewton, but it's Newton per coulomb. I already put 10 to 3 as a factor for reflecting this kilonewton. Okay, so what is the potential energy of the system if you put a dipole into an electric field? If you know the orientation of the dipole, if you know the direction of the electric field, we know that the system has the potential energy, and that potential energy is given by just dot product of these two vectors, the dipole vector and the electric field, but we have a minus sign in front of this dot product. So keep this in mind. So obviously this potential energy depends on the orientation of these two vectors, but in order to rotate the dipole so that it becomes parallel to the electric field, this is the initial orientation, potential energy of the initial orientation, and this is EI, and the potential energy for the final orientation, let's put P final dot E. Well, the only change with the initial orientation and the final orientation is that the dipole, for example, this picture reflects the initial dipole, but the dipole becomes parallel to the electric field. That means in that case the dipole is just parallel to the x-axis. This reflects in the energy, potential energy, given in the second expression, U final, and this is the potential energy of the initial configuration. So of course there is a change in the potential energies. In that case, the change in the potential energy is going to be reflected on the work to bring the dipole from this orientation to this orientation. It is nothing but the change in the potential energy. So that means U final minus U initial. Okay, this is the expression for the work needed to be done to bring the dipole initially oriented in this direction to this direction, to this orientation. So all you need to do is just calculate these dot products with the final orientation and the initial orientation, and take the difference. That's it. All right. So what is the final potential energy first? Well, it is, since the dipole is just parallel to the electric field, this dot product is nothing but, since also we have minus sign over here, the magnitude of the dipole vector multiplied by the magnitude of the electric field. That's it, right? And since the angle between them when they are parallel to each other is 0, cosine 0 is 1, so we don't need just to put cosine 0 over here, which is already 1. So it's enough to put P times E, as the magnitude, but we have also minus sign coming from the formula for the potential energy. And minus this minus this again, P times E, all right, magnitude, but this time we have to also put the cosine of the angle between them for the initial configuration. But in the initial configuration, the dipole is making 30 degrees with the electric field, so we have to put the cosine 30 over here. So this makes, you can take the parentheses P and E, right, magnitudes of dipole and the electric field, minus 1 minus plus cosine 30 degrees. So this is it, okay? This is the thing that you have to calculate and to find the work. Of course, this is work in units of joules. Just put the P, which is 17 times 10 to minus 3 times E, 87 times 10 to 3, 10 to power 3, right? And minus 1 plus cosine 30 degrees. So obviously this is going to be, this expression, the work for the expression is going to be negative because cosine 30 is some number less than 1, between 0 and some positive quantity, but it is going to be less than 1. But we have minus 1 over here, so this parenthesis is going to be a negative quantity multiplied by this. Work is not going to be negative. So what is that means? What does that mean, that to have a negative work? That means that the system itself will do the work to bring the dipole from this initial configuration to the final configuration, so that the dipole is just parallel to the electric field. The electric field does the job. If you have a negative work to bring the dipole orientation from this to this one, you don't need to do work, but the system itself does the work. That's why we have a negative quantity as a result of this calculation. Okay, and I'm just leaving the calculation to you. It's just a multiplying the numbers and adding this minus 1 and plus cosine, and multiply this all these three numbers to find the result.